As promised, the new section is entitled Conditional Distribution, but the continuous case. Let's make this bigger. Okay. So let's suppose that x and y are random variables that have a joint PDF f of xy. So we are going to talk about conditional distributions, continuous case. Now, if x and y have a joint probability density function f of xy, then the conditional probability function, the conditional probability function of x, given that random variable y is equal to little y, is the following. It's going to be f sub x given y of the value of capital X, comma, the value of capital Y. And like always, this is going to be the probability of x and y divided by this one, divided by the probability of our script f of y. And of course, this is assuming that the denominator is not 0. You can't divide by 0. We're not going to get into that. Okay. Now, I'm going to build up something. So we'll talk about in general. If A is any set, A is some set, A is some set. And, like it says above, x and y are jointly continuous. Jointly continuous. Then, what is the probability that the random variable is an element of the set A, given that y equals y? Well, y is a constant and x can change. And what does x come from? It comes from A. So we're going to integrate over the set A of what else but this function right here. F sub x given y of little x, little y. Now this little y is a constant. It's that y value. And x is changing. I'm going to add up all the probabilities for x, but y, while y is being held constant. Y is not changing. Okay. So let me keep this bottom on the board, which means I need to write on the top. Now, what if we wanted to do or find the formula for the cumulative function of x given y, say at the point A? Okay, yes, I can say at the point A. Now, let me just erase this a little bit better, please. Come on. Okay. So, what if the set A is all the values below some little a, even including little a? It's not going to matter whether we include it or not. So, f sub x given y of a given y is equal to the probability that x is always less than or equal to a, given that the random variable y is always equal to little y. So we have that. But now, what is this? Well, this is the integral, since x is always less than a, the integral from negative infinity to a, y is held constant. So it's going to be times, or the integral of, f sub f x given y of, that should be in x, because we're integrating over x's, x comma y, but x is changing, y is not, hence dx. And that would be the definition of the cumulative function of x given y. F sub x given y. All we know is that y is constant and x is not. Okay, let's work out a couple of problems. That's how you learn math. You study this theory and you work problems. Some people like to do this theory first and then do problems. Other people do it in reverse order. The joint density of x and y is given by little f of x, y is equal to, and usually it's a piecewise function. Sometimes it's 15 over 2 x, 15x over 2 times 2 minus x minus y. And this is true only when x and y are both between 0 and 1. And it equals 0. Otherwise, it equals 0 everywhere else. So what is the conditional density function of x given that y equals y? And y will be between 0 and 1. Compute, find the conditional density with an I in it, the conditional density of x given that the random variable y takes on the value little y. And I really should say that y is in between 0 and 1. Okay, so now let's talk about that. For y between 0 and 1, what is f sub x given y of x comma y? Well, using the definition, it's nothing more than f of x comma y. And of course I have a silly error here. It's little f. It's f of x and y divided by f of y. F sub capital Y of y. And this is equal to f of x, y over, well, this here is the integral, the bottom, this is the integral from negative infinity to infinity of our f's, well, actually, no, it's going to be the integral of the PDF. It's going to be the integral of f of x comma y, but only x's change. Okay, the numerator, this piece right here, is given it's given right here is going to be this. It's going to be 15x over 2 times the quantity 2 minus x minus y. This is if x is between 0 and 1. Otherwise, it's going to be 0. Otherwise, this numerator will be 0. It tells me right here, f of x, y is 0. If the numerator is 0, forget about it. The fraction will be 0. We're assuming that this bottom is not 0. Okay, and the bottom is going to be, well, most of the time, like I said above, that's going to be 0. In fact, only when x is between 0 and 1 will it not be 0. So we're going to integrate f of xy, which we're going to integrate this function with respect to x going between 0 and y. Now, remember, if both x and y are between 0 and 1, we get this rule. But if none of them, if x and y only have 1, if only x is between 0 and y, but let me say that again, if only x is between 0 and 1, and y is not, that's the otherwise case, and we get 0. If y is between 0 and 1, but x is not, we get 0. Because to use the top rule, both x and y have to be between 0 and 1. I'm sure most people will readily agree that if neither x and y are between 0 and 1, then we get 0. That is why to compute the conditional density of x, given y equals y, we really want to say y is between 0 and 1. Because if y is not between 0 and 1, then the answer is always 0. Because the numerator, this numerator, will always be 0 if y isn't between 0 and 1. Okay, so only talking about okay, I guess I have a silly typo here. I should be saying for x between 0 and 1. We already know that y is between 0 and 1. Okay, so now let's see what we get. Distributing, the 2's are going to cancel. We get 15x minus 15 over minus 15xy over 2. Coincidentally, that's what this in the bottom. It's this. So I'll integrate that with respect to x. And then I get 15x squared over 2 minus 15x cubed 6 minus 15 squared over 4. The bottom, and only the bottom, gets evaluated where x goes between 0 and 1. Only the bottom does that. Okay. Let's raise actually the bottom. Extended integration. And though you might want to say that is Calc 3 integration only because we're integrating with respect to x and there's y's in it. Alright, so the top doesn't change. It's 15x minus 15x squared over 2 minus 15xy over 2. The bottom. First you plug in 1 for x. So you're going to get 15 over 2 minus 15 over 6. 3 goes into both of those numbers 5 times and 2 times. So you get 5 over 2 minus 15 times 1 squared is 15 times y is 15y over 4. And when you plug in 0, since each term has an x in the numerator, you're going to get 0. Okay, I guess what I would do at this point is I would multiply top and bottom. To get rid of the denominators, I'd multiply by 4, and 5 goes into each of the numerators. So I'm going to multiply by 4/5. And I have no idea why the beginning didn't come out. So I'm going to copy this down. 15x minus 15x squared over 2 minus 15xy over 2. Okay, and that's the second time it didn't come out. 15x, put that eraser down nicely. 15x minus 15x squared over 2 minus 15xy over 2. That's the numerator. And when you plug in 1 into the very bottom equation, when you plug 1 in, you just get everything but the x's. Because x to any power is x, and when you is 1, x to 1 to any power is 1. And when you multiply by 1, don't bother. You still get to anything. And then when you plug in 0, you get 0. Okay. Now, when it comes to all the denominators, 4 is the first common multiple. So that's what motivates me to multiply top and bottom by 4. Why do I also divide top and bottom by 5? Because 5 goes into the top and the bottom. 4/5 times 15x. Well, 5 goes into 15 3 times. 4 times 3 times x minus. 5 goes into the 15 3 times, and 2 goes into the 4 2 times. So we get 6x squared. And the next one is just arithmetic. We get 3xy, or basic algebra at least. We get 3 times xy. And for the denominator, goes in 3 times, 2 goes into 2, 2 goes into 4 2 times, you get 6 over 2 minus 3y. Okay. All right. Now, I can factor out as 3 from the top. 3 times 4 is 12 times x is 12x minus 3 times 2 is 6 times, actually, I'll factor out as 3x. 3 times negative 2 is negative 6, and the x in front times another x gives me 6x squared minus, I have this 3x, I just need the y. And I divide this by, well, 6 minus 2 is 4 minus 3y. There is your answer. Let me write down the bottom. 4 minus 3y. Okay. Let's try another one. So basically, other than using basic calculus integration formulas, we just have to know the formula for their joint density function. Alright, suppose that the joint density of x and y is given by the following. f of xy is equal to a piecewise function. Sometimes it's e to the negative x over y times e to the negative y. And this happens as long as x and y are positive. And like most times, we'll define it as 0 otherwise or elsewhere. So now we want to find the probability that x is more than 1 given that y is some value bigger than 0. Bigger than 0. Because again, only when x and y are both positive do you get this. That is, when x and y are not both positive, you get 0. There are 4 cases. X and y can be positive. X can be positive, but y is not. Or x can be negative, but y can be positive. Or both x and y can be negative. If x and y are not both positive, this is the only case where they're both positive. These 3 cases are not both positive. Okay, so if you're given this case or that case, notice that y is less than 0. Okay, what is the probability that, well, actually, you probably could do that. What is the probability that x is positive? No, you can't. What's the probability? Well, you can do it easily. It'll be 0. That's what I meant. What's the probability that x is positive given that y is negative 2? Well, if y is negative 2, you're always going to have f of xy being 0. Okay, but it's not necessarily always the case. Let's erase this and move on. So, exactly what does this mean? This is equal to the integral x goes from negative infinity of f sub x given y of x given y, but only x is changing, or x comma y. Only x is changing. So, but basically, to do this problem, we need to figure out what that is. That's what we need to figure out. Fx given y of x given y, little x given little y. Well, by definition, this is f of x and y divided by f of y. But we write script y because there are 2 random variables in this case. And we know the numerator is outright given to us. It's e to the negative x over y times e to the negative y. Or it's 0. Or it's 0. So we're only talking about when x is 1 or bigger, which lives in here. Okay, now, what is the bottom? What is the bottom? Well, the bottom is the integral from 0 to infinity. That's what x goes from, of f of xy dx. Of f of xy dx. But we know that, actually, if you want to be exact, it's from negative infinity to infinity. But we know 2 things. We know maybe 3 things. We know that this bottom is 0 when x is less than 0. If you're not between 0 and infinity, you're less than 0. Okay, it's 0. Is that a problem? Oh, you can't divide by 0? No, because we're really going from negative infinity to infinity, which is the integral from negative infinity to 0 plus the integral from 0 to infinity. Now, fine, this here is 0. That's 0, fair enough. But this is not. So when you add them up, you will not get the number 0. Okay. Because the second integral is always positive. So when you add it to the positive quantity to 0, you don't get 0. So we go from 0 to infinity. Another thing we know is we know what f of xy is in this interval from 0 to infinity. It's e to the negative x over y, e to the negative y dx. Now, I want to remind you that if you have the integral of e to any constant times x dx, this integral is just what you started with, and then you divide by the constant. And that's it. Okay, let's see if I can sneak that in somewhere. The integral of e to the kx dx is what you're integrating divided by the constant. Okay. So that's done. The next comment I want to make is, let me move this over a little bit. Okay. It's the integral from 0 to infinity. And the comment that I want to make is, e to the negative y, having nothing to do with x's, I can put in front. Okay, so we have e to the negative x over y times e to the negative y, that's just the numerator, divided by the constant e to the negative y times this integral. But e to the negative x over y, oops, what am I doing? Well, I guess I didn't need the integral. E to the negative x over y is the same as e to the negative 1 over yx. Its power is a constant, negative 1 over y, times x. So I know the antiderivative. I know how to integral e to the negative x over y dx. It's just what I started with, e to the negative 1 over y, or e to the negative x over y, times divided by the derivative of that power, divided by negative 1 over y. And this bottom goes from, x goes from 0 to infinity. So, the negative 1 over y, let me be sure about this. I multiply, it's going to go to the top as negative 1 over y, e to the negative x over y, e to the negative y, over e to the negative y, e to the negative x over y, but that bottom goes from 0 to infinity. Now, the 1 over y I brought on top could have been dangerous if it had x's in it. Because remember, these are x values. Okay, so this canceled out, but notice, I will not cancel out the e to the negative x over y's, because it's not a constant. That's going to be a numerical value. So I get negative 1 over y, e to the negative x over y over. Now, if you plug in infinity for x, you have e to the negative x over infinity. You have e to the negative infinity over infinity. Well, this is 1 over e to the positive infinity over y. That power, remember, y is bigger than 0. That power is super large. Infinity over y is very large, and e to very large is enormous. And 1 over super large is 0. So when you plug in when you plug in infinity, you get 0. Minus. Now I plug 0 in. Negative 0 over y is 0. e to the 0 is 1. So this bottom is negative 1. And when you divide negative 1 over y by negative 1, you just get 1 over y times e to the negative x over y. Multiplying by 1 over y is the same as simply dividing by y. Okay, so now, remember, we were trying to figure out what this equals, and we just did. This is equal to e to the negative x over y all over y itself. Okay. So let's erase all this work we did just to find the piece of that integral that we were stopped at. And so all of that was like side work, or a major problem, or a major part within this problem. So this is the probability that x is bigger than 1, given that y equals y, is equal to the integral from 1 to infinity of this, which we just put a lot of energy into finding out. It's e to the negative x over y divided by y dx. Okay. Now this y in the bottom, I can pull out as 1 over y. And remember, negative x over y is negative 1 over y times x dx. If I know that integral, the 1 over y stays. The integral to e to a constant times x dx is e to the constant times x divided by the constant. Divided by the constant. And this is going from 1 to infinity. Okay. Negative 1 over y cancels. Dividing by negative 1 just changes the sign. That is, you can get rid of the negative and just put it on top. This is what we have. Now, I personally hate negatives when I have to plug in limits. So I ignore the negative, but then I have to switch the order of the limits. I go from infinity to 1. And remember, those limits are x values. When you plug in the x value, you get e to the negative 1 over y. And when you plug in infinity for x, well, we just did that. It's 0. And when you take away 0 from what I just boxed, you get what I just boxed. So the probability is the probability, so let me write it down here. The probability that x is bigger than 1, given that y is random variable y, script y, big Y, is equal to some number between 0 and 1. Here's the answer. Between 0, bigger than 0. Bigger than 0. Y is bigger than 0. So if y is 7, the answer will be e to the negative 1 over 7. That is, the probability that x is bigger than 1, given that y is identically 7, is going to be e to the negative 1 over 7. Okay. So erase this, try something else. Okay. What if x and y are independent, continuous, random variables? Then, what's the following? Then, their conditional density of x, given that y is equal to little y, it's just going to be basically it's going to be f of x. Okay, no one would, if it's independent, if x and y are independent, then knowing the value of y doesn't help you at all. Doesn't matter what y is. And the proof is straightforward. F sub x given y of x given y. Well, this is f of x and y divided by f of y. You know, I can write it different. Well, okay, so now since x and y are independent, the numerator is just f of x times f of y. Another way of writing this bottom is just f of y. Or if you prefer another way of writing that top, is this way. And this cancels out. And all you have is this. It's just the probability that x equals little x. And that's what happens when they are x and y are independent. That finishes this section.